Children, our today's topic is determinants. Suppose there is a matrix A. It's a square matrix, and we have to. Matrix is arrangement of numbers, and we have to convert it into determinant to calculate the value of this arrangement. So we cannot calculate the value of any matrix. Okay, this is just an arrangement. So if we have to find the value of this matrix, then we have to convert into determinant. Then we can say that the value of this determinant could be either real number or it could be imaginary number, right? Determinant of matrix. Suppose there is a matrix A, then determinant of A. Determinant can be represented as determinant of A. We can write it as DETA, delta, or if A is a matrix, then determinant of A can be represented as like this. This is not a modulus, children, because here A is not any number. A is a matrix, right, children? Now take another example. Suppose A matrix is A, B, C, D, right? So the determinant of A will be, we remove these braces, these brackets, and we write it like this, A, B. Now we can expand it. When we expand, then the value of this determinant will be the product of these two numbers minus these numbers. So determinant of A will be AD minus BC, right, children? Determinant will always be square. Only square matrix can be converted into determinant. So determinant will always be square. Note down, please. Now, children, we study about minors and cofactors. Suppose there is a determinant A which have row 1, A1, A2, A3, second row is B1, B2, B3, third row C1, C2, C3, and we have to calculate the minors of this determinant, right? Suppose we are calculating the minors about row 1 minors. Minor of element first row, first column. This A11 represent, this is the minor of element first row and first column. So what we are going to do, we are going to leave this first row and first column. So when we remove this first row and first column, what will we get? This determinant B1, B3, C2, C3. So when we expand this determinant, what will get? B2, C3 minus C2, B3 or B3, C2, right? Now, when we have to calculate the minor of A12, that means the minor of element first row and second column. So what we are going to do? We are going to leave this first row and second column. So what will be remaining? What elements will be remaining? B1, B3 and C1, C3. Right, children? So we are going to represent it in a determinant form. So when you expand this determinant, what will get? B1, C3 minus B3, C1. Right? Similarly, this one. Now suppose we have to calculate the cofactor. For calculating the cofactor, then the formula Cij is equal to minus 1 to the power I plus j into Mij. This C representing cofactor and this M representing minor. Right, children? So suppose we are calculating the cofactor of first row and first column here. Now the value of I here is 1. The value of j here is 1. So what you are going to do? We are going to put 1 and 1 in place of I and j. So when you substitute the value of I and j as 1 and 1, so it will become minus 1 to the power 1 plus 1. We know minus 1 square is plus 1, right? And minor of first row and first column is this. So the first cofactor and minor for the first row and first column is same. Now see cofactor of first row and second column. So here the value of I is 1, the value of j is 2. Right, children? So minus 1 to the power 1 plus 2, that will be 3, and minus 1 to the power 3 is minus, right? The minor of first row and second column is B1, C3 minus B3, C1. So the minor value we have already calculated, just put it here, and with the minus sign, this will become the cofactor. Right? For calculating cofactor, children, remember this. This is the sign criteria for 3 by 3 determinant. Right, children? So whenever you have to find the cofactor, just calculate the minor and follow this sign. If this cofactor you are calculating, that means here you are getting minus, here you are getting minus, here you are getting minus. This is the third row, second column. So these are the elements we are getting minus, rest all are positive. Right children? Note down please. Now children, see if you have to expand this determinant A, which has first row as A1, A2, A3, B1, B2, B3 as second row, C1, C2, C3 as third row. Then you can see here the expansion of this determinant will be A1 into the cofactor of first row and first column. Suppose here I am expanding this determinant about first row. So I have written A1, this is the first row and first column element. So it will be multiplied into the cofactor of same place, that is first row and first column, plus A2 cofactor of first row and second column, A3 the cofactor of first row and third column. Children, you can expand this determinant about any row and any column or any column. It will not affect the result of the determinant. You can expand about first column, second column, third column. Okay. So if you put the values of this cofactors here, it will be A1. So this row and this column will be left out. B1, C2 minus C2, B3. This place will be negative. As I told you, minus, 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 4 minus we are getting here and here and here. Right? So minus A2. This row, this column and this row will be left out. B1, C3 minus B3, C1. Right children? A plus A3, B1, C2 minus B2, C1. So this will be the expansion of the determinant. Okay children? Now you can see one sum here, one example for expanding the determinant. It is like x square minus x plus 1 into x minus 1. Here we are having x plus 1 and here we are having x plus 1 again. Suppose you have to expand this determinant, find the value of this determinant, then what we'll do? We'll find the product of this minus the product of this. It will be like x plus 1 into x square minus x plus 1. Right? Here we are getting x plus 1 into x minus 1. We can easily see there is a formula written here. This is the formula of a cube plus b cube, that is b is here 1 and a is x, so it will be x cube plus 1 and this is x square minus 1, right children? So what we are getting here, x cube plus 1 minus x square again plus 1. So what we'll get, result we'll get x cube minus x square plus 2. Right children? So now we know that how to calculate the value, how to expand the determinant. Please note down. Children, now we study about some properties of determinants. So pay attention because these are the properties that will help us to solve the sums. Okay. So first property states that if all the elements of any row or column in the determinant are 0, then the value of that determinant will be 0. Suppose this, see you can see here, I have taken an example in which determinant first column, all the elements of first column are 0. So the value of the determinant will be 0. Directly we can use it. Suppose you expand this determinant about column 1. So the expansion will be 0 into cofactor of 1, 2, 0 into cofactor of 2, 1, second row first column, and 0 into cofactor of 3, 1. So 0 into anything is 0. So all the three elements will be 0. So the value of the determinant will be 0. Okay. So whenever you see all the elements of any row or any column are 0, then the value of the determinant will be 0. Okay. I am mostly taking 3 by 3 order determinant because higher determinants are not in your syllabus. Okay. So we only stick with the determinant of order 3 and less. Second property states that if each element of one side of the principal diagonal are 0, then the value of the determinant will be the product of the elements of the principal diagonal. Anywhere you can see this is a principal diagonal, right children? you can see there the elements, all the elements of principal diagonal, here you can see all are 0. So according to the property, we can say that the value of the determinant will be 2 into 3 into 1. Let's see how. Suppose we expand this determinant about the first column. So the expansion will be 2 into this row and this column will be cancelled. The cofactor of first row and first column, that will be 3 minus 0. So you can see here the value will be 6, and 6 is the product of the elements of principal diagonal. Right, children? Note down please. Children, now let's see property 3 and 4. Property 3 states that if we interchange rows and column of a determinant, the value of the determinant remains unchanged. Right, children? Suppose I have taken an example, that means interchanging rows and column, that will not affect the value of the determinant. Suppose any determinant A, it has first row 3, 4, second row elements 2, 1. When you expand this determinant, it will be 3 1s are 3 minus 2 4s are 8. So 3 minus 8 will be minus 5. Now interchange the rows and column. You can see here the first row has become first column and the second row has become second column. Right, children? Now when we expand that, the determinant what will get? 3 1s are 3 minus 8. Again we'll get minus 5. So we can say that on interchanging the rows and column will not affect the value of the determinant. Now see property 4. Any row or column of the determinant are interchanged, the sign of the determinant changes. What does that means? It means that on changing any particular row with any other row, it will be minus sign of the whole determinant. The minus sign comes out. See, suppose any determinant I've taken 2 0 1 first row, 1 0 2 second row, 3 1 0 third row, and I have interchanged the row R1 and R2. You can see here second row has become row R1, first row, and the first row has become the second row. That means first and second row are flipped, interchanged. So what will happen? It will be minus times of the value of the same determinant. Right, children? Note down. Now children, see property 5 and 6. It states that if two rows or columns are identical, then the value of that determinant will be 0. Right, children? That means if any two rows or any two columns are identical, we can directly say that the value of that determinant will be 0. See, I have taken an example here. Row 1 is and row 3 are same. Okay. So when you subtract these two rows, you will get one row, all elements 0. So according to property 1, the value of the determinant will be 0. You can see here. So whenever you see any two rows or any two columns same, straight away write the value of that determinant will be 0. Right, children? Now see property 6. Property 6 says if each element of a row or column of a determinant is multiplied by a constant, say lambda, then the value of the determinant is multiplied by the same constant. Let's see how. I've taken an example. I've taken a determinant A, which is 2, 1, 3, 4. And when we expand this determinant, what we'll get? 2, 4 the 8, minus 3, we'll get 5. Right, children? Now we multiply this whole determinant by the value 4. So when you multiply this determinant 4, what we'll get? Again, we'll get 20. That means 4 times the value of the determinant. So you can see that by that property, the value of the determinant will also be multiplied by 4 if we multiply any constant in any row or any column. Right, children? Note down please. Now children, we obtained one result by using property 6 that any term can be multiplied in any row or any column, that will not, the determinant will also be multiplied by the same term. Suppose there is a matrix B which has the element A1, A2, A3, B1, B2, B3, C1, C2, C3. So determinant of B will be again A1, A2, A3 but in determinant form. Suppose there is a matrix A which is K times of B. So the matrix A will be K into the matrix B, which is A1, A2, A3 B1, B2, B3, C1, C2, C3. Right, children? Now, when we convert this this multiply K into this matrix, we know that it will be multiplied with all the elements. So it will become K A1, K A2, K A3. Similarly, K B1, K B2, K C1, K C2, K C3. Right, children? Now, when we find the determinant of this matrix A, what will be the determinant? You can see that it will be K A1, K A2, K A3, K B1, K B2, K B3, K C1, K C2, K C3. Right. Now you can see that K can be we can take common K from row 1, row 2 and row 3. So K into K will be K cube will come out, and what we'll get here inside the determinant A1, A2, A3, right, children? Now this is what? This is determinant B. So determinant A can be written as K cube of determinant B. Right, children? So we can say that if the order of the if the order of the determinant is n, here I have taken 3 order matrix, so we are getting 3 K cube. If we have taken n order matrix, it will be K to the power n. So we can say that determinant of KB will be K to the power n into determinant of B. So where n is the order of the determinant. Right, children? We are going to use this result to solve sums, right? Please note down. Children, let's see few more properties. Our next property states that if some or all elements of a row or column of a determinant are expressed as sum of 2 or more, then the determinant can be expressed as the sum of 2 or more determinants. Suppose we have any determinant A, okay, and you can see that this row 1 has elements A plus B, C plus D and E plus F. That means there is a sum of 2 elements here we are getting in row 1, and so this determinant we can write as these 2 determinants. So when we expand these determinants and add, and the result of this determinant will be same, okay, by property 7. Right, children? Next, property 8 states that if each element of a row or column of a determinant be added the equi-multiple of the corresponding element of 1 or more rows or columns, the value of the determinant remains unchanged. What does this mean? Let's study one example first. Suppose this is a determinant A which has row 1 as 2, 3, 4, second row is 1, 2, 1, third row is 2, 2, 3, right, children? And we are multiplying with a scalar term of 3 in R2 and then adding with R1, and the result is written in R1, right? So if you multiply 3 in R2, so 1 3 is a 3, plus 2, 5, right, children? 3 2 is a 6, plus 3, 9, 3 1 is a 3, plus 4, 7. So the question says the value remains unchanged. That means the value of this determinant and the value of adding and multiplying with a scalar term will remain same. Now we will solve this determinant and see whether we are getting the same determinant again or not. Right? So you can see that this first row, the elements of first row can be written as 5 can be written as 2 plus 3, 9 can be written as 3 plus 6, then 7 is 4 plus 3. Now by using this property, we can separate these 2 determinants. So this will be 1 2 1 2, 3 2 2 and 4 1 3. Okay, and the next determinant will be 3 6 3 in first row, 1 2 1 in next row, and then third row is 2 2 3. right? So this is our determinant A. Now when you solve this determinant, when you take 3 common, what will happen? The first row and second row will become identical. So the value of this determinant will be, children, 0. That means A determinant plus 0 will be the value of the same determinant again. So this property is true then. The value, when we multiply any scalar term or add with any other row and column, the value of the determinant that we obtained will be the same as the original determinant. Right, children? Note down, please. Okay, children, let's see property 9, which states the sum of the product of the elements of any row or column with the cofactors of the corresponding elements of some other row and column, right, is 0. Let's try to understand by taking simple example. What does this property means? This property means that suppose if we take any row, if there is any determinant A like 1 2 1 3 0 2 2 2 1, right? This means that if we take the elements of first row and we add with the product of the some other row or column. Suppose I have taken the cofactors of third row. So when we multiply the cofactor and the element and then we add, the result will be 0. So for this determinant, let's see if the property is true or not. So I have taken this A11, this is first row, first column element. So I am multiplying with the cofactor of third row, first column. Third row, cofactors of third row. So this will be like this, A11, C31. This is cofactor of third row, first column. First row, second column element. Cofactor of third row, second column. First row, third column element into cofactor of third row, third column. So you can see that A11 is 1 and the cofactor of this term will be this row and this column cancel. This row and this column cancel. It will be 4 minus 0. It will be 4. 4 1 the 4. Right? Now if you see this, for this A12 is what? 2 we have. And when we take the cofactor of this third row, second column, children, this column and this row will get cancelled. 2 minus 3 will be minus 1. So this place has minus sign. So it will be plus 1. So 2 1 the 2 will get. Now when you see this place for this product, first row, third column into the cofactor of third row, third column. So first row, third column we have element 1. If you calculate the cofactor of third row and third column, what will get? This row and this column will get cancelled. 1 minus 6. It will be minus 6. So you can see clearly the result is 0. Hence this property is true. We have verified this property. Next property states that if any A and B are a square matrix of same order, that means if A is order 2, then B will be order 2. If A is 3 order, then B will be of 3 order. Then states that the determinant AB will be determinant of A into determinant of B. Another property, and we discussed by taking simple example. Here I have taken a matrix A as 1 2 3 2 and matrix B as 3 4 5 2, right? So you can see that both are second square matrix of order 2. So when we multiply this matrix AB, what we'll get? We'll get 13, 8, 19, 16. Right? We know how to multiply. You do the multiplication, we get this matrix AB. So if you calculate the value of the determinant of A, what we'll get? 2 minus 6, that will be minus 4. Determinant of B, what we'll get? 6 minus 20, that will be minus 14. And determinant of AB, when you solve, it will be 13 into 16 minus 19 into 8, that will be 56. So you can see that the determinant of AB has value 56. And the determinant of A, when you do, determinant of A into determinant of B, when you multiply, what result we are getting? 4 into minus 14. This is again 56. So we can say that we have again verified this property that determinant of AB can be written as determinant of A into determinant of B. Right, children? Please note down. Children, we can also calculate the area of the triangle by using determinants. We say that if A x1 y1, B x2 y2 and C x3 y3 are the vertices of the triangle ABC, then the area of the triangle will be we can write as 1 by 2 into determinant x1 y1 1, x2 y2 1 and x3 y3 1. When you expand this determinant, we'll get this formula 1 by 2 x1 y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2. Children, we know that when the 3 points are collinear, the area of the triangle formed by those collinear points will be 0. So when the area of the triangle is 0, that means the 3 points are collinear, right? And when they are given collinear, then the area will be 0, vice versa. Right, children? Note down, please. Now, children, let's see. The question is, show that the points 1, 0, 6, 0 and 0, 0 are collinear, right? We have already discussed when the points are collinear, that means the area of the triangle is 0. So, for proving that the 3 points are collinear, we have to prove that the triangle that they are forming has area 0. We know that the area of the triangle formula is 1 by 2 x1 y1 1, x2 y2 1 and x3 y3 1. When we substitute the value of x1 y1, x2 y2 and x3 y3 from here, what we'll get? We'll get a determinant in which first row is this, second row is this, third row is this. Now you can see in this determinant that the second column elements are all 0. And first property states that if all the elements of any row or any columns are 0, then the value of the determinant will be 0. So we can directly put the value of determinant as 0 without expanding. 1 by 2 into 0 will be 1 by 2, hence the points are collinear.